as Wojtek said, I will tell you something about modeling wind effects on buildings, and also, of course, about modeling wind effects with fires. I will start from the basis. You have to know that to perform CFD simulations, we need some basic values like wind velocity, wind direction. We need to know what is the period of time that we are taking our initial data from and how we will assess them later. And of course, we need to know what part of the domain of interest is. In our case, when we want to take the wind velocity, first thing is to reach for the Eurocode, where we can find some basic wind velocity values. But of course, those basic values are quite high. For Poland, our three wind zones, we have values from 22 to 26 meters per second. But of course, those values are only basic characteristic values, and if we want to take into account mean velocity, we have to modify those fundamental basic wind velocity with also the change in the height, and of course with the effects of terrain roughness and orography. And if we do that, we have to check in what kind of terrain we have. We have 4 different terrain categories, and then we can choose one of those values. In our case, we decided to perform our calculations for the 4th category. This is like the city center with high buildings, and based on that, mean wind profiles can be assessed. So here we can see 2 ways to represent those wind profiles that we will put as inlet values for the calculations. And of course, they are different for different terrain categories, and we can choose one of them. So, of course, we have to also decide what will be the wind direction. So there was a meteorological study done for the Warsaw area, and the data that we have from the meteorological stations were limited to 5 stations, and we took the 10-minute average speed of the last 10 minutes of each hour. And the speed was with the resolution of 1 meters per second. And also some gusts were recorded from the last 10 minutes of each hour. And those values can be seen here on those graphs. The blue one is the maximum value, so those are those gusts. And the red one is the mean value. Taking this whole data, we made 9 groups of wind velocities, but we will only focus on the 3 of them. So we have the velocities 3 meters, 5 and 7 meters per second. This is prevalent values for all the cases where the mean value is 3 meters per second. And we, of course, have to choose the wind direction. And those directions were put into wind sectors from 12 wind sectors. And for those 3 wind velocities and of course one smaller 1 meter per second, the probability of occurrence of a given wind speed was done, and this was calculated as a total number of records in the considered measurement period. We have the occurrences of the all given speeds, and because of that we could make the analysis based on some real data with probabilities. And the next step we've done during the simulation was to choose the area we were interested in. So we chose a city environment in Warsaw with the height of the buildings up to 48 meters. And the radius was 420 meters. Here you can see all the buildings, and on the right there is a little part of it. In the middle you can see a little red building. This is domain with the in the middle that we will put our main interest building there. So the next step is to bring this real model into the computational domain. So we have to take into consideration that this domain has to be built in a way that will not create any blockage. And therefore, the domain was quite huge. We had some values here on the graph that show how many heights of the highest building have to be maintained to have no blockage in the domain. And this is the real domain I've created. And it consisted of 3 zones. In the middle, there is a zone with the car park. And in this zone, we can put various different buildings. There is a circular zone that will have all the explicitly modeled buildings, and the rest is the square zone with the external boundaries. Of course, the next step was to create the mesh, and I used the surface grid extraction technique by Blocken, because this is the technique that that using this technique we will be certain that the wind flow is not disturbed by any mesh. It's a hexahedral mesh mainly in the whole domain, and the car park or the buildings in this little subdomain in the middle are built with the tetrahedral cells because of the level of detail that is needed. And here you can see how this mesh looks like. On the left with all the buildings, you can see that those buildings were extracted from the ground, and actually there are no all of those buildings are a little simplified because of this extraction technique. We had to choose what level of details we have to maintain. And on this picture, you can see the yellow subdomain in the middle. And in our case, we have the open car park. And, but of course, in the future, this subdomain has 48 meters. So we can put any building or object we want in the middle and check how the flow will change or any other parameters we would like. And of course, we can check the environmental effects of wind. And of course, all of the simulations have to be validated and verified. So we can validate our model, CFD model, with the wind speed distribution and mean wind speed values with the experimental data. And this is the model that was scaled to 1 to 200s. And we cannot scale down the fire. So therefore, we can only check the wind profile and average wind statistics in this validation. And of course, I've done the verification of the CFD model with the grid sensitivity, and turbulence models were also checked. And there were some discrepancies in the results because there was a problem with atmospheric boundary layer speed up at the bottom of the domain. So this is the ABL homogeneity problem. We have the unintended streamways gradients in the approach flow because we have to set some kind of inlet flow that is at the inlet plane, but we have to maintain the same values in the incident flow also. So the flow that is the closest to the considered building. And as you can see on the right, the problem with the speed up with those change in values is a known problem that was countered by many scientists. And in our approach, I was able to use modified wall function, which was based on the aerodynamic roughness Z0. And this was used instead of equivalent sand grain roughness, which is used usually in the standard wall function. And this allowed us to have no speed up in the wind profile, no change between the inlet profile and incident profile. And also the application of driving shear stress was set at the top boundary of the domain to also maintain the same profile as at the inlet. So here are the results from my ABL homogeneity test. On the left, there is a standard wall function. On the right, modified wall functions. So for the standard wall function, we can see how the wind profile changed along the length of the domain. And it can be seen on the bottom image. And we were able to get very good values of similarity between the incident and inlet profiles for the wind velocity and kinetic turbulent energy, and also the dissipation of the kinetic turbulence energy. So after doing the ABL test, I was able to put a fire in my domain. But of course, it wasn't literal fire, and I had to simulate it as a volumetric source of the heat and mass. And no chemical reactions were actually modeled. But the heat transfer was, of course, applied in the model. And the simulations were, of course, done as a transient flow and with the Ran's equations and RNG turbulence model. I would like to summarize how this was done, because maybe it will be easier to get a grip about this. So at the beginning, it was the geometry import, and I had to do the import of the whole domain with the explicitly made buildings. And then was meshing, building the case in the Fluent, assigning the interfaces, of course, and at this point, making the ABL new wall functions definition. And then I could go to the next step, CFD calculations. And those were repeat steps, because we had different cases with different wind speed and wind direction. And those calculations also had the fire in them, and they were done for different heat release rate. And in the post-processing, you have seen some of the data. We can take the temperature, smoke, velocity, statistics, and see all the important things as a data or as images. Overviewing the whole project, we've done in the main series 336 simulations with the open car park and the implicitly modeled area of the city. And the additional series had the warehouse instead of the open car park in the middle subdomain. And the additional series B will have 144 simulations with the open car park, but the city modeled explicitly. And in all those cases, you can see that we had various heat release rate, wind speed, and 12 angles of wind attacks for each of them. Here are some results of the wind speed distribution inside our open garage. So you can obviously see that for the angle of the wind attack equal to 0, the wind goes through the building, and the velocity inside is higher with the higher velocity at the inlet. But for the 90 degrees, where we have a wall from the incident flow, there is a stagnation point observed, and it's in there even at the highest velocities with 7 meters per second. And when we look at the visibility of smoke inside the car park, so on the left, for the 0 degrees, there is near perfect outcomes for all the fires, because the smoke is blown out from the car park, And for the 90 degrees, the smoke accumulates and doesn't leave the car park. And this is this can be seen for all of the heat release rates, but the most significant for the highest one. Of course, we modeled the surroundings of the building to check how they will impact the flow inside our car park or other buildings. So in this case, you can see how there is an unexpected flow path on the right, on the bottom picture, where the flow changes and there is it will influence the outcome of how the fire will behave inside the building. This is the building of the warehouse, and this is how the wind behaves inside. We can see the vortices inside the building, and even the small change of the wind of the wind angle can change how this wind will behave inside the building. And of course, the similar results for the car park, and those velocities inside the building may also help to assist the evaluation of conditions. Of course, we can think that even without the fire, we can take some knowledge from this simulation and make some assumptions.